So now we're going to look at, so before we just talked about the existence of, say, some K coloring on some graph, and kind of the implications of that, color criticality, everything else. So now we're going to talk about how many, given a certain graph and given, some K, how many different ways can we properly color that graph with that specific K? So not necessarily K equal, say, to the chromatic number, but just some arbitrary K. So we'll define this function chi of G semicolon K as the number of ways to properly color some graph G with, obviously, K colors. So obviously this is going to be a non-zero function if the chromatic number G is less than or equal to K, because obviously if our K is less than the chromatic number, that function, so if chromatic number of G is greater than K, that would just imply that this would always be equal, oops, not 1, equal to 0. So let's think about this function. So again, this defines the number of ways, given some graph G, that we can properly color that graph G with K separate colors. So first, let's consider click K sub n. So if we were to consider basically, let's start out with a triangle, and let's say K equals 3, n equals 3. How many different ways can we color this triangle? So we're going to consider a possible color set here of 3 possible colors. And so if we were considering, say, coloring any arbitrary vertex, so, essentially we can select any arbitrary vertex to start with. So what we're going to do is randomly select some vertex, color it with one of these colors, and talk about the ways, different possibilities, I guess, we could have here. So let's start out with just coloring this vertex. So we can color it either red or blue, color 2, or with our third color. So there's, for that vertex, without loss of generality, the first vertex we select, as all vertices are essentially automorphic to each other, first vertex we select can be colored with 3 possible colors. Say next, we considered coloring some separate vertex. We can color it with every color except the one we originally colored that first vertex with. So we color it with color 2 or that first color. So in other words, 2 possibilities. And then going back to our first or our final vertex, we are only left with that one final color we didn't use. So in other words, the value of this function for the graph K sub 3, so triangle, and our K equal to 3 is equal to 6. So we had 3 possibilities for that first, 2 for the second, and 1 given K equals 3. What about if, say, we had 4 possible colors? So same idea. This, instead of 3, 4 possibilities. Now we can select any color except the color that was used on the first one, and right there. So you should be able to see a pattern here. And the pattern basically being K times K minus 1 times K minus 2 equals chi K sub 3. Okay, so generalizing this function to specifically K3 for some general number of colors, we see that it's just simply we can select any color. Hypothetically, for this first vertex, we color as all vertices are connected to each other necessarily, regardless of the second vertex. We can color it with all colors except that first color we used, likewise for that second. So to generalize to any arbitrary click, so not just case of 3, but case of n, essentially we're doing this, but instead of, say, 3 terms within this function, we just have n terms. So we can generalize this to any arbitrary click. So k times k minus 1 times k minus 2 times k minus 3 dot 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 up to k minus n plus 1. So likewise with this first, when we were first considering the triangle, k minus 3 plus 1 equals k minus 2. So essentially this gives us the number of different ways that we can properly color any click. So let's consider tree T now. So we can kind of consider this from somewhat of a same perspective. So if we consider, say, coloring, let's root our tree. So this will, without loss of generality, this will be a reasonable argument we could make. So not weighted or anything. We're just considering some arbitrary root to our tree. And maybe we have something like this. So this, just a general arbitrary tree. So this same argument could be generalized to any tree, no matter what. The root could be, just a leaf or anything else. So if we consider, say, coloring a tree, let's say we know a tree is bipartite. We talked about that. So it can be colored in at least 2 possible colors. But let's consider, say, 3 possibilities right here. So again, for our root, we can color this with any arbitrary color we select. What about the colors on, say, that first level down from the root? If we would say let's consider this vertex first, like we talked about with click, here we only have 1 color used. So like considering back to that second vertex that we colored within the click here, we're considering the fact that we can color this vertex now with any color except that used by the root. So we color with the second color or color with the third color. Likewise, exact same thing for this vertex here. We can color it with first color or second color. So right now we have k possibilities for our root, and then essentially k minus 1 and k minus 1 for our 2 vertices on that second level. And now let's go down to the next level. This vertex, we can color it red, we can't color green, or we could color it blue. So we can color this vertex essentially any color except for the color of its parent. Same argument we can make here, this vertex, and this vertex. So really the only thing we're constrained with, and even coming down here to these final vertices, we can color them with any color except the color of its parent. In other words, we're only constrained when we're doing this arbitrary coloring by the color of that vertice's parent, and this will retain a proper coloring where we have for each vertex except the first vertex we color, k minus 1 possibilities with k, that first vertex we color, possibilities. So to generalize this to any arbitrary t, any arbitrary k, where k is greater than or equal to that chromatic number of the graph, is k for the root, or really it doesn't need, since without lots of generality, it could just be any arbitrary vertex within the tree that we could select as a root for this hypothetical kind of structure we approached it with. So k minus 1, and then n minus 1, where obviously n is just equal to the cardinality of the vertex set of our tree. So again, the argument we're making here, we can color that first vertex with k possible colors, and for every other vertex, all n minus 1 other vertices within our tree, we can color it with, we're only restricted by one single color, essentially. So these functions have a specific name for them. In the general case, these are called chromatic polynomials. And essentially, obviously, general form, pretty much what we saw before, is just this, essentially chi of g semicolon k, essentially the number of ways to color g with k colors, obviously. So the general form specifically, if we're trying to actually explicitly determine that chromatic polynomial, so we kind of saw, you know, some structure to when we talked about trees, when we talked about clicks, but there's a more generalized form for any arbitrary graph. And so here we're going to say that this is the sum n, where r equals 1, this p sub r of g times k sub r. And so here we have essentially a polynomial with terms p sub r times some k sub r, which we will define. So our p sub r of g, consider this as the number of ways to partition g into r independent sets. And our k sub r is equal to the number of ways to color the independent sets. So our k sub r, going back to what we saw for the click, where we have n, essentially n vertices, each vertex is just by definition of a click, and the fact that we have connectivity to every other vertex within the click. So we have n independent sets. So we kind of see that equivalent kind of structure for defining this k sub r. So k minus r, to generalize it, instead of n vertices, we're talking about r independent sets now in general case. So this k sub r is going to be irrespective of the structure of the graph. It's only a function specifically of k and of r. But that p sub r is kind of going to be dependent specifically on the graph itself. So if we go back to a click, so let's consider defining this specifically for click in terms of the, let's talk specifically, say, for k sub 3, we're going to construct essentially the chromatic polynomial and note its equivalence to that first form that we talked about. So, k sub 3, let's say, just for simplicity, 3 colors first, equals sum over n, r equals 1, p sub r, k sub n, or let's make these explicit, 3, k sub 3, and k of R. So we're summing, so let's consider for R equals 1. So R equals 1, the number of different ways we can partition G into R independent sets into one independent set. 0. So this is R equals 1. And why is that 0? Well, like I said, with a click, every single vertex has to be in its own independent set. So essentially, the only way, so the minimum piece of R that we're going to be non-zero for is going to be 3. Basically, if we consider any arbitrary non-empty graph, it's going to be impossible if at least one single edge exists for this piece of R function to be equal to greater than 0 if there exists any arbitrary R, or any arbitrary edge, because that edge will restrict us from having those two vertices in the same independent set, effectively. Likewise, for this specific instance, we're going to have 0 for R equals 2, but for R equals 3, so if we consider for R equals 3, specifically on this click, if we consider the number of ways to partition K sub 3 into R independent sets, since each vertex is connected to every other vertex in the graph, we're considering 3 independent sets naively. Each vertex goes into its own independent set necessarily. So for that, our piece of R for R equals 3 is just equal to 1. And then for those 3 independent sets, the number of ways to color those independent sets is just 3. So considering each independent set, so considering some first arbitrary independent set, which is just going to be a single vertex in this instance, but it could be multiple vertices in the general case. For 3 possible colors, we can color that, every vertex in that independent set. Again, in this case, just a single vertex. In the general case, it could be multiple vertices, but we're coloring all of them the same color of 3, K equals 3 possible colors. The next independent set, 2 possibilities, final independent set, 1 possibility. Or if we're just considering, so here that obviously the value of this function, the value of the chromatic polynomial, actually solving it out explicitly like this, is equal to 6, or if we just generalize it again, essentially k minus 1 dot 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 k minus, since it's only going to be non-zero for r equal to n, k minus n plus 1 gives us the general form for click. So same thing that we kind of deduced before, but here we explicitly solved it out on, considering explicitly the chromatic polynomial and how it is specifically structured. Okay, now let's consider an example on some tree. So for simplicity, we'll consider this tree, which is essentially just a path graph on 3 vertices. So that'll be our T. So let's kind of solve this out too for this tree specifically, and let's do it for an arbitrary K. So this is equal to the sum over n, R equals 1, P sub R of T times K sub R. And n is just going to equal 3 in this instance. So again, let's solve it out here. So for R equals 1, since we have at least one edge in this graph, we can't place all vertices into that same independent set, because by the fact that an edge exists, they're not independent. So that'll be a 0, and irregardless of what K sub R is, that's going to be 0 for that term within the summation for R equals 1. So for R, what about R equals 2? So here, if we would consider, say, placing this vertex into independent set 1, this vertex independent set 2, this vertex must go into independent set 1. So realistically, and it doesn't really matter the labeling specifically, we're only considering essentially membership in this partition per vertex. So there's only one way that we can say partition these vertices into that independent set, into two independent sets. So for that 1 times our case of R function, so remember in the general case, we go k times k minus 1 dot 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 k minus R plus 1. So here for R equal to 2, we just have k times k minus 1. And then what about for R equal to 3? So again, really we only have one way that we can partition these vertices, just putting every vertex into its own independent set. Recall at least how it's drawn up here with 1, 2, 3. So 1, 2, 3, that they all are going to be in independent sets, and doesn't matter what the labeling is. There's just only one way, vertex time each vertex into its own non-empty independent set. And so same idea, times k minus 1 times k minus 2 for R sub 3. So if we solve that out, we have k times k minus 1 plus k times k minus 1 times k minus 2, which equals k squared minus k plus, let's say, k squared minus k times k minus 2, which equals k squared minus k plus k squared plus k cubed, let's see, k cubed minus 2k squared minus k squared plus 2k. And let's reduce this, k cubed, so minus 3k squared plus k squared, so minus 2k squared minus k plus k. And so if you recall from what we had with the tree specifically, so where was that? All the way up here. K times k minus 1 up to the n minus 1. So what we would expect is this in fact let's equal to what we have before, k minus 1 times k minus 1. So let's just solve it out. K squared minus k times k minus 1, which equals k cubed minus k squared. So k cubed, oops. So k cubed minus k squared minus k squared plus k, which equals k cubed minus 2k squared plus k. So these two are in fact equivalent. So I call this, we ended up here from what we had originally by, essentially the term k minus 1 up to n minus 1, which we kind of deduced by looking at the structure of trees and how we color them specifically. And this first version is what we ended up with by actually explicitly working through this chromatic polynomial in the general form for the tree, kind of right up here. So we have equality, so it looks like the math checks out. All right, that's what we like to see. Okay, so before, when we were talking about the number of different ways, spanning trees and everything like that, the number of different ways to, the number of different spanning trees arbitrary graph might have, we looked at this kind of recursive type relationship. And so there's kind of an equivalent idea in terms of the chromatic polynomial of a graph. And this is called the fundamental reduction theorem. And the basic idea, so let's take a look at what it actually is. So the chromatic polynomial of a graph, so we're going to refer to this now just as the chromatic polynomial now that we know what it is and what it means and everything. So the chromatic polynomial of an arbitrary graph G is equal to the chromatic polynomial of a graph with an edge removed with the same number of possible colors k minus the chromatic polynomial of a graph with that edge contracted. So chromatic polynomial of G is equal to the chromatic polynomial of G minus E for any arbitrary E within the edge set of G minus the chromatic polynomial of G with that same edge contracted. So consider, say, let's specify that E edge within the edge set, E equals UV, which is within the edge set of our graph G. So any arbitrary edge, I mean, really we could say for any edge within the edge set, this holds. So let's think, so before we were looking kind of at the number of different spanning trees and that kind of recursive type relationship, we kind of were able to justify it by looking at the individual components in terms of how we say recurse. So let's look at this first. So G minus E, K. So this, if we consider removing some edge E, the chromatic polynomial, really the number of different ways we could color G, we can say that this is the number of ways to color G such that the color of U equals the color of V, or the color of U is not equal to the color of V. So why this is, obviously that seems fairly obvious, but the reason why this is useful is if we consider, say, edge contraction, this is the number of ways to color G such that the color of U equals the color of V. So when we consider, say, an edge contraction, or U, V into, let's just say, U prime. So here, if we're considering, say, deleting this edge, we can have U and V different colors, or same colors, again, with this edge removed. But if we contract, we're kind of restricted to having that as a single color. So again, this is kind of in the context of the whole neighborhood. So in effect, what this is really saying is the number of different ways we can color G is essentially the number of ways we can color G with U and V having the same color or a different color minus the number of ways where they have the same color. So effectively, that just leaves us, if we consider this whole side, that just leaves us with the number of ways that we can color G with them having a different color. And so again, this recursive relationship allows us to essentially, recurse until we get to a point where we know the chromatic polynomial of, say, the underlying graph. So like when we're subtracting or contracting, eventually we'll get to, like we saw before with counting the number of spanning trees, get to a point where we have some closed form solution. So really, at least in this instance, the closed form solution we have, at least so far, are for cliques and trees in general. So let's take a look here at, say, what is the chromatic polynomial of C5 given some k? So there is a closed form solution for cycles. That's pretty straightforward. But here we're going to use the fundamental reduction theorem to determine the chromatic polynomial. So again, we're looking at some arbitrary edge deleted and contracted. So if we say consider our edge here, this equals the chromatic polynomial with that edge deleted minus the chromatic polynomial with that edge contracted. So right away, we have a tree right there, a tree on 5 vertices. So we can reduce that, k minus 1 to the 4, and then minus this, but we can again apply our fundamental reduction theorem. So considering this is our edge E in this instance, another tree minus polynomial of 3 cycle, aka a clique of size 3. So equals k minus 1 to the 4 minus, so another tree, k times k minus 1 to the 3 minus our 3 cycle, which we know, k minus 1, k minus 2. So solve it out, k minus 1 to the 4 minus k minus 1 to the 3, and then plus, so some 2 subtractions there, k minus 1, k minus 2. And then we could actually, if we wanted to, reduce that into some simpler form possibly. But what we're going to look at here is how can we get a chromatic number from the chromatic polynomial. So here we have some chromatic polynomial for some graph, in this instance 5 cycle. And so considering just the chromatic polynomial, how can we get a chromatic number from it? So basically one way to do that is, so for all possible k, which is the first non-zero for, this is for any arbitrary chromatic polynomial. So essentially, if we're considering all possible k, so k equals 1, k equals 2, k equals 3, eventually we're going to get to some k equal to n, or let's say k equal to x, where the chromatic polynomial, if we plug k into, say, what we have above, will be non-zero. So if we consider that polynomial, chromatic polynomial, really just the polynomial itself, and we try to, say, solve for k equal to 0, obviously 0 times 0 minus 1 to the 4 is just 0 times minus 0 plus 0. So obviously 0, and we know we can't color a graph with just 0 colors anyway, so that's pretty trivial. But what about for 1? So that would be 1 times 0 minus 1 times 0 plus 1 times 0 times negative 1, which is just 0. What about k equal to 2? So again, we have 2 times 1 to the 4 minus 2 times 1 to the 4 plus 2 times 1 times 0. So these two cancel out. The first two terms cancel out. The last one is just 0. So again, 0. And now what about k equal to 3? Let's try her out. So 3 times 2 to the 4, so 2, 4, 8, 16, minus 3 times 2 cubed, which is 8, plus 3 times 2 times 1. So that'll equal 48 minus 24 is 24 plus 6 equal to 30. Now it's not a proof, so let's give her a check mark. So in this instance, this implies chromatic number of G equals 3. Just by the fact that, well, not just this by itself, this final k equals 3, but the fact that k equals 0 is 0, k equals 1 is 0, k equals 2 is 0, k equals 3, non-zero, implies that the minimum for which, the minimum k for which the chromatic polynomial has a, non-zero solution, or essentially 30 different ways to color for k equals 3. Essentially, that just tells us that since that's the minimum k, that's also correspondingly the chromatic number. And since we're working with a 5 cycle to begin with, we already know that for a cycle that's even, its chromatic number is 2. For a cycle that's odd, its chromatic number is 3. And for a 5 cycle specifically, we also correspondingly know there's 30 different ways to color a 5 cycle with 3 different colors. That's essentially what we're looking at here.